Okay, so hi everyone, I'm Gergerdi, and I'm going to talk about pattern synonyms, which is a language extension to Haskell, currently implemented in GADT. So first thing I'm going to talk about is what are pattern synonyms. So let's start with an example. So suppose you have you're implementing a language, and it's a very simple language with very simple types. You only have monomorphic types. You don't even have meta variables, and you want to come up with a representation for types in this language. So you might say, okay, so a type is a type constructor applied to a list of type arguments. This is a very nicely generic representation of a type in this example. You can write generic traversals transformations around it. But of course, there are going to be types which will have some special meaning for you. So for example, if your language includes, let's say, arithmetic, then you are going to talk about the integer type, and you're going to talk about functions over integers a lot in your code. So you can create functions which abstract the construction of this representation. So here we see that tyInt abstracts the construction of the type which represents integers, and macFunType is a function which abstracts the creation of a function type from the argument type to the result type. So and then once we have these functions, we can combine these functions without any reference to the representation of our data type. And we can say that the type of plus is a function from int to int to int. And these compose just as well as the real constructor would. So the idea behind pattern synonyms is to give you the same ability, to give you the ability to abstract matching, give names to special kinds of matching in the same way, so without changing the representation. So in this example, we create a pattern synonym for function types. We say that funty is a pattern which matches an arrow type and then matches two patterns against the two arguments of the function type. And using this pattern synonym, here we can write a function which takes apart a function type into a list of argument types and then a result type by just pattern matching on this pattern synonym, which means that it reads exactly how you would want to read it if you could change the representation, or if you wanted to change the representation for this particular function. But of course, by not changing the representation, you retain all those other generic traversals over this type. So the goal of pattern synonyms is to bring this tool of abstraction that we already have for construction in the form of functions and bring it to pattern matching. So as you can imagine, it's quite a cross-cutting change to Haskell or to your Haskell implementation. So in GADT specifically, it basically touches all parts of the front end. So obviously you need parser support and renamer support for it because you need some syntax for these pattern synonyms. But also it requires changes to the type checker. That's something that I'm going to talk a lot about later. It requires changes to the desugarer because, of course, if you have a pattern matching which is defined in terms of pattern synonyms, you need to be able to compile that. And it required changes to interface file handling because these pattern synonyms, if they are to be proper abstractions, they should be exportable and importable. On the other hand, on the backend side of GADT, as we will see, and this is the other thing that I'm going to go into in depth, the desugaring is such that on the backend side, there are no changes required. So the first thing I'm going to talk about is pattern types. Why is this an interesting question, given that Haskell has had patterns and pattern matching for ages? But before the addition of pattern synonyms, the patterns were only typed implicitly because you will have typing rules for a case expression, you will have some typing rules for defining a function via pattern matching. But in all of these cases, you will always only talk about exactly saturated patterns, right? So the question of what is the type of just some part of a pattern on its own, it just didn't come up before. So the goal of the typing here is, again, in analog, we can say our goal analogously to functions in that we want to assign some kind of type to pattern synonyms so that when you use one, we can tell if that use is well-typed or not just by looking at the type without having to look at the definition of the given pattern synonym that you're using. So our requirement on whatever we come up with as a type for patterns is to enable this. So let's look at some examples to try to map out the problem space. So of course, the first thing we can notice is that we want to know what the scrutiny type of a pattern synonym is, because when you pattern match against something, that's going to be required. You don't want to allow matching a pattern synonym which is defined as, I don't know, unit against a term of type or a value of type int, right? So here we can see some pattern synonyms, and as you can imagine, the type of the scrutiny is not going to be really surprising. In the first case, it's bool. In the second case, it's maybe bool. And of course, we can have universal quantification. So in the third example, when we define a pattern synonym as nothing, we can say that this is a pattern synonym that you can try matching against values of type maybe A for any choice of A. Of course, it makes sense to allow for parametric pattern synonyms, just like in the Fantai example that I included in the motivation. So in this fourth example, the pattern synonym P4 takes another pattern, and that pattern will be used in subsequent matching of subparts of the thing that we are matching against. So in this example, and we will use function, the function type syntax for this. So in this example, we will say that P4 has type A to maybe A for all A. So again, this means that given a pattern which matches things of type A, P4 of X will match values of type maybe A. So, and then you could think that, okay, so like that's it. We have something similar to functions. It's going to be good enough because now we have patterns and we have parameters in them. However, it turns out that we need more than that in Haskell. So in these two examples, the first one is an overloaded literal, and the second one is a view pattern. So in both cases, these are polymorphic patterns, but these are restricted there's restricted polymorphism going on here. So in the first example, we need num and eq instances to be able to do the comparison. And in the second example, we need a show instance to be able to apply the view pattern on the scrutiny. So we see here that for certain patterns, we will have constraints which are required to be able to do the pattern matching. So here we see these included in the type. And then turns out that there's another kind of interplay between type classes and pattern matching. So in this example, which doesn't use pattern synonyms, right? So this is a vanilla GATT, Haskell plus some GATT extensions code, which uses a GADT where the constructor has an existentially bound type variable, B, and it has a constraint on the constructor, EQA and show B. So what happens when we pattern match on this constructor? So when we do that, we bring into scope both a rigid type variable B and the two instances EQA and show B. So in this example, on the right-hand side, we use equality between two A's, and we use show on the B. But the type of F is still just for all A, T, A to maybe string, because by matching on this constructor, it provides us these type class constraints. So, of course, by analogy, that means that if we define a pattern synonym which abstracts away this constructor, then it too will bring in both the rigid type variable and these provided context. So we will need to include that in the type of the pattern synonym. So here, what we see is that in this case, we have a universally bound type variable, and we have an existentially bound type variable, and we have some context which is provided by this pattern synonym. So the syntax that you can see here it shows both the required and the provided constraints with the usual double arrows separating the two, and then the rest uses the function type syntax for the arguments and the scrutiny type. Of course, you can have required and provided contexts at the same time. So here's an example where matching on P requires an EQ and the num instance on A because it uses an overloaded literal on at a position which is typed A in the constructor. However, the constructor mucti that we match on provides EQA and show B instances. So in this case, we will assign to P the type for all A such that there's a num instance for A. This is the required constraint. It provides some rigid type or some existentially bound type B. It provides the type class context EQA and show B. And in this context, it has one remaining argument, which is a B, and the scrutiny type is T of A. So notice how, because matching on mucti provides EQA, and matching on P requires EQA, the EQA constraint doesn't show up in the required constraint of P because that one is satisfied by mucti itself. So it makes no sense for it to show up in the required constraint because that would make it too constrained. If you were to inline this definition of P into use site, it's not true that you would need an EQ instance at that point. So putting the typing all together, what we see and what we have found is that you actually need 6 different axes to fully specify the type of a pattern synonym. So on one hand, you have the universally bound type variables, the required context, and the scrutiny type. You can think of this as the outside view or the match-oriented view of it. And then you have the existentially bound type variables, the provided context, and the types of the parameters. And the first 3 are with only the universally bound type variables in scope, and the other 3 are with both the universally and the existentially bound type variables in scope. Again, this is basically the same as how when you make a GADT, any type variable which shows up in the type of the constructed thing will be universally bound, and any type variable which only shows up in an argument will be existentially bound. So putting these 6 axes together and coming up with a surface syntax, because we needed both so that GHC can report these types and also so that the user can give type signatures to pattern synonyms. So we are using the syntax that you can see there. Of course, the usual shorthand notation applies as well. So you can omit the binders. So you can implicitly qualify your type variables. That one uses the same rules as the GADT syntax. And if the provided context is empty, you can omit it. If both the required and the provided context are empty, you can omit both. If only the required is empty, then you can't, because you have to disambiguate between the required and the provided context. So yeah, so much for typing. And now that we have our well-typed pattern synonym applications, how do we compile it? So the idea, and so this is using the same example as before, the most complex one we've seen, use it deliberately. so that we can see how the types will match up. So the basic idea is that for each pattern synonym definition, we generate a matcher function, and then usages or matching against that pattern synonym will compile to calls to the matcher function. So the matcher function is something which takes 3 arguments: the scrutiny, which of course has the type as it was described in the type of the pattern synonym. And then it takes 2 continuations, a success continuation, which gets everything which is provided by the match, i.e. the existentially bound type variables, the provided context, and the subterms which match the parameters, and then gives you some result. And then there's a failure continuation, which doesn't get anything, it just gives you the result. And then we do the obvious thing of just running the pattern match and seeing which one to call. So the nice thing about this is that this can be represented with GHC core without any change whatsoever. So that's what I meant by the backend doesn't need to be changed. And that's useful because it means these are exported and linked and optimized just like any other function. We attach unfolding, like GHC has this concept of unfoldings, which basically means that in the interface file, you can also get the definition of the function. So we attach that to these matchers. So GHC can, the GHC optimizer can decide to inline these, in which case it becomes completely free from an operational standpoint to use the pattern synonyms. So that's nice. I was simplifying this somewhat because if the result type is unboxed, you need to do some magic. You need to add a artificial argument just to keep laziness, but I'm not going to get into that. But one thing which is important to mention here is that, so pattern synonyms are proper abstraction. They are not just macro substitution, and their semantics is not just the semantics of macro substitution. So the difference is that the full potentially nested structure of the pattern synonym is matched first, as we saw here, and only then do we care about the rest of it. Only then do we pass the subterms to the success continuation to do its pattern matching. So in this example, we have F1 and F2, which both try to return true on the singleton true list and false otherwise. But one of them is written using straight pattern matching. The other one uses a pattern synonym for singleton lists. And here what we see is that the one on the left, so F1, is strict in the element, in the first element of the list. So if you have, like here, right? If you have a list which contains 2 bottoms, then this will first match the outermost cons. Okay, it's good, we'll go on. And then it will try to match the true against the bottom, so we get bottom. Here, if you first do the full matching here, then what happens is that, okay, is it a cons? Yes. Is it a cons something nil? No, it's not. So this one fails. It doesn't even look, it doesn't get here. It doesn't look at the first element because the cons something nil, like the outermost structure is matched first. So this will be more lazy than this one. One could think, but it's not true because we can also find other examples where F1 is more lazy because here, if I make a list where the head element is false and the tail is bottom, then this will fail. So it's a cons, yes. Is the first element true? No. So this one falls through here. Whereas here, is it a cons something nil? Well, is it a cons something? Yes. Is the tail nil? Well, no, it's bottom, so this will diverge. So, so here we can see that we can't really say that using pattern synonyms makes your program more lazy or less lazy. You just have to understand that it has different dynamic semantics because I think it's unavoidable. I think it's a feature. It's not a bug because it's defined as something which either matches fully a singleton list or it doesn't. So that's basically it. Just to give a bit of history, so all this, well, the feature of pattern synonyms itself was the proposal was added to the GHC wiki in 2011, and then in 2014 I added them to GHC 7.8, by which I mean I coded up an implementation using basically macro substitution, and it kind of worked for like Haskell 98 programs, and I thought, okay, it's basically done. And that's when we found out, when I tried to integrate it into the larger context of, of what GHC has, that's when we found out that there's all this subtlety around the typing of the pattern synonyms. And then in 7.10 and 8.0, there's been incremental improvements to it. And as of June this year, we found 72 packages on Hackage which are already using pattern synonyms. Of course, we have a lot more detail in our paper, lots more examples. We talk about pattern synonym directionality, which I couldn't talk about here, but basically the idea is that if you have a pattern synonym, it looks sufficiently like you were also constructing the thing in an expression context, right? Like deconstructing and constructing can be each other's duals if certain extra conditions are met. It talks about record syntax support, which I have not talked about, but it's a new addition in the 8.0, in JC 8.0's version of pattern synonyms. And we have a formalization of pattern types without any proofs, but at least we have a type system with Greek, so that if you want to build some more work on top of this, then you can use it as a baseline. And that's it. You can find my slides and you can find our paper at that URL. Thank you.
Okay. Thanks, Gerger. Any questions?
Yeah, so the thing that you said, it's a feature, not a bug. I don't see that yet. I mean, it looks like a bug to me, just from the point of view of reasoning about it. Can you justify why on earth you'd want it to behave the other way?
So, okay, but when you say that reasoning about them is hard, that's because you want to reason about a usage of a pattern synonym with knowledge of the definition.
But that's, I mean, just about everything in Haskell, you have the equivalent of something like beta reduction, and now you're telling me, but on the patterns, you don't have beta reduction. You're not allowed to expand the pattern without changing the behavior of the program. No. Oh, okay, Simon. Go ahead.
So in the Haskell report, the semantics of pattern matching are given by saying in a compositional way that says if you've got a pattern of the form constructor applied to P1, P2, P3, then you evaluate the thing. If it evaluate the value of matching against, if it's headed with constructor K, then you match each of the subpatterns. And to give a compositional account of pattern synonyms in the same way, in the same style, you need this thing, right? You have to say to match against a pattern synonym P. What you do is you first match the value against the pattern given in the pattern synonym definition, and if that succeeds, you then match against the subcomponents. So to give a compositional account in the same style as the report requires this semantics. That's the best way to
So that has a superficial plausibility about it, but yeah, I mean, obviously there's more discussion. I'm still not compelled, but it's lovely work. Everything else about it.
We have time for one more question.
G'day, Matt Roberts. I'm really curious about the performance of code written with this, not from the point of view that I think it's going to be bad, because I take the point you made in the paper about it generally being okay, but just from the point that there's an opportunity to compare with Haskell, which isn't available in other languages with fancy pattern matching, the non-synonym version versus the synonym version. Has any of that been done?
Well, not by me. I don't have an answer for you. I think like you could argue for inlining every function everywhere ever and not using functions anywhere, because then you omit the overhead of a function call. But we still use functions because they're nice abstraction. I don't know, because I'm not that much into operational stuff.
Yeah, maybe how can I clarify what I mean? It's not that I think you want to be compiling those things away. It's that I'm curious from an empirical point of view, just to kind of put a pinpoint down and tell people when we go to pattern synonyms, the amount of overhead is X. And we're perfectly happy to pay that because this is a great abstraction, but I'm curious to know the quantum.
Okay, I don't have an answer for you, but it's not going to be like, so the overhead is going to depend very much on the interaction with generic core optimizer passes. Mm-hmm. So
yeah, it's only something we can work out empirically, probably.
Okay. Let's thank Gergo again.